Hi everyone. Not that big a crowd, but it's okay. More intimate environment. Okay, so my name is Davin, and I'm a tech lead at Airbyte. I'm responsible for the cloud, infrastructure, and tooling portion of Airbyte. So this is something I worked on about a year ago. I think it's a very neat solution to sort of solving this problem. And yeah, I'm very excited to tell everyone about it. So let's begin. So a quick overview of what we're going to cover today. We're going to start off with what is Airbyte, right? Don't worry, not a sales call, mainly to set the context of what problem we're tackling, our constraints, and hopefully help everyone understand the eventual solution. Then we're going to talk a bit more about the naive approaches to solving something like this. We're going to go into a bit detail on two of these approaches, right, which, although they are naive, they do apply in certain situations. And then finally, spend most of our time talking about what the title of this talk is about, which is using socat and a bunch of Linux tools to sort of scale CLI composition on Kubernetes. And hopefully do a live demo, which I will not mess up. Great. So really quickly, what is Airbyte? So we are an open source framework for solving syncing data, right? So we are focused on the EL of ELT, basically moving data from one system to another. And this is challenging, and there are two main challenges with something like this. The first one is the number of integrations you would have to support, right, as you want to move more and more data. So very simply, this diagram just illustrates it. If you have M sources and destinations, now this quickly becomes a polynomial problem, right? Where you have to understand every single connector or integration that you need to use, understand, develop, and maintain. And so that is difficult. This is my obligatory bad joke. The rock is crushing it, and the money debt. So this leads to bad tech debt. Second problem here is the reliability of scheduling. So as data becomes much more of a critical business need, it is very important that the data arrives on time in the format that you want. And this is not an easy problem because there are many different flavors of schedulers, right? You have your cron strings, orchestrators, all the way to what we call today workflow orchestration engines. This is a very large tech space with a lot of complex operational learnings. And it's not easy for any engineering team to understand all the trade-offs, pick the right technology, and learn how to operate it. So those two problems, right, number of integrations, reliability of your scheduling, usually makes engineering teams very sad when they think about this. And really, for most companies, this is not a core competency. What you want to be focusing on is actually extracting value out of the data and not wrangling it. So how Airbyte solves this is two ways, right? One, we have an Airbyte protocol, right? And this is a JSON-typed container interface. So anyone can sort of contribute a container. As long as it fulfills the Airbyte protocol, we will run it. And we bundle that with a development kit to make container contribution as easy as possible. So the idea here is to really crowdsource the first problem away. We also provide within the platform a scheduler and a UI. So we do the hard work of making all of that reliable and making that usable for non-technical users. So that's a whirlwind through this problem space and what we do. And the important thing to focus on is the Airbyte protocol. Just to restate, it is a JSON-type container interface for integrations. And the other thing to focus on is the fact that we started with a Docker deployment, right? So these two things, and I'm kind of building up to the rest of the presentation. So let's do a quick dive into how Airbyte Docker works today. This is a very simple diagram. There are boxes on the screen. The important boxes are the blue-colored boxes, right? You have three of them. They represent processes running on a node that are backed by containers. The brain of this, the most important process, is the worker process. What that does is orchestrate and do bookkeeping. So what is happening is it is creating a source process that is reading from a source, and then creating a destination process, writing to a destination, and then orchestrating all of it to happen correctly. So all of this is actually hidden behind an actual process interface. Our backend is in Java, so this is actually a code snippet where what I just described sort of happens in code. You have destination start and source.start. And so because these are all processes, now we can do process-like things with them. Right? We can read the output streams, read the error streams, and then pipe data in. And so I've kind of sort of been building up to sort of the abstract of my talk, which is the way we think of data integrations at Airbyte really is composing CLIs. And I sort of just walked through what we have in our example, a read CLI and a write CLI, and we have something sitting in the middle orchestrating that. So these CLIs can come from different vendors. In our case, it comes from Airbyte, and we have the Airbyte protocol defining the CLI interface, right? But here's an example of a CLI command that doesn't come from us. In the red text, you have a read command, right, that comes from Postgres. We're reading from Postgres, and then gzipping it. And then in the blue command, you have an AWS command, right? We're writing it to AWS. So in totality, read CLI reads from Postgres, write CLI writes to S3. So this mental picture is great and very simple, easy to reason with until it doesn't. And what we saw with users, open source users, was that any users running about more than 1,000 jobs a day started hitting vertical scaling limits. There's only so much 64 cores and 128 gigabytes of RAM can actually get you. It is massive, but there is a limit. And so about a year ago, we sat down and started thinking, okay, we're seeing this limit. How do we horizontally scale this sort of model of thinking? And obviously, we chose Kube because Kube has great mindshare, very battle tested, very well known in the community. So that brings us to the problem statement, like I promised, not a sale call, which is how do we dynamically orchestrate CLIs on Kube while making no assumptions on the container runtime? Right? No assumptions because of the Airbyte protocol. We want to make it as easy as possible for anyone to contribute connectors or integrations. So to clearly state our constraints here, again, we have no container assumptions. We want an easy way to reason about the scaling, right? It can't be sort of too operational, it can't be too slipshod. And lastly, we want it to be compatible with the existing Docker deployment. Ideally, this happens at the infrastructure level and plugs into existing code, and the actual code execution path is agnostic of what is being swapped out behind a process interface. Cool. So now that we have sort of talked about the problem, defined it, let's briefly talk about naive approaches, like I said. So the first approach we looked at was kube jobs. For people not familiar, Kubernetes offers its own job primitive. The problem with it is not exactly suited for critical workflows. It's much better for cleanup tasks, sort of sweeping tasks. There's a lot of documentation online. Won't go into it, but I'm happy to chat more after this. Second thing we looked into was Lambda functions. I think serverless is very hot. It still is kind of hot. And this is basically trying to convert all our jobs into serverless functions running in public clouds. Now, the big problem with this is serverless functions usually have a time limit, right? And so in GCP's case, that is 60 minutes. And that would be limiting our job execution to 60 minutes. That's fine, but that's not really something we want to take on when we're executing jobs. Oh, sorry. The last two approaches, naive approaches, are a bit more interesting, and so we're going to talk more about them in detail. So the first one is what we call Docker and Docker, right? And how this works is basically you set up your kube cluster in a way that you have access to the underlying Docker agent. Right? And this means the containers running or your pods running now can use that Docker agent to dynamically create like container processes. And so this works exactly identically to how Airbyte Docker works today, which is what I showed a couple of slides back. So why this doesn't work very well in practice is it is a huge security risk. What you're essentially doing is setting up your infrastructure to arbitrarily execute containers at runtime, which is even worse than arbitrarily executing processes because containers can contain anything. And more importantly, this is not actually supported by public clouds. Again, because it's a huge security risk, and it also breaks Kubernetes abstractions, right? Kube puts in all these walls in place for a reason. The last thing is, because your containers are local processes now, we kind of go back to vertical scaling constraints. We have to make sure the nodes can fit all containers a job pod might run, and that's not what we want. This is valid in certain cases, right? This is fine if you operate your own kube cluster, so you can actually create that security hole. And if you have very stable workloads, so you can size your nodes appropriately, and you have vetted containers, right? In our case, we offer something what we call custom containers, so we don't have the opportunity to vet all the containers running in Airbyte. So the last sort of naive approach I want to talk about is what we call like pools of job pods. How this works is you have per connector or integration job pod pools, and all of these pods are waiting around to perform a certain task, right? And so going back to the CLI example, if let's say your orchestrator or the worker needs to do something, it just reaches out to one of these job pods and says, hey, read this data for me, or write this data for me. There are a lot of ways of implementing this. It's kind of a huge space as well. We're not going to have time to talk about it today. This is a bad idea because it costs a lot of money. You have all these underutilized pods lying about. And more importantly, it's not a scalable approach because it means that now you have one pool for each connector or integration you want to support. And we want to support as many as possible, so it's inherently not scalable for us. Because you have a whole bunch of pods just lying around, it's also operationally very challenging. Your kube cluster is now the base load of your kube cluster is very high, and so you have to work through a lot of noise and a lot of logging when you're operating it. And it's really more of a tactical rather than a sustainable approach to solving this problem. However, this is appropriate, right, if you have very stable workloads, so you can sort of avoid the problem of underutilized job pods, and you have limited job types, so you can avoid sort of that operational complexity with running all these empty pods in your clusters. So this kind of, as we work through this, we thought to ourselves, okay, what is our ideal solution, right? What we really want to do is dynamically create these pods and hide these behind our existing process interface. And so this is great because we only create the pods when we need, so we don't have any underutilized pods. We avoid all that cost. And it ideally fits well with a Docker approach. Right? Again, I mentioned, we want to minimize tech debt. So I'm going to walk through this solution just in little bite-sized problems. I think that's kind of how software engineers think. Take a big problem, cut it down, compose it back up. So this is problem 0, not because I'm counting from 0, but because it's really not a problem, right? It's like a non-problem. And that is how to dynamically create pods. This one is easy. Kube has a great API, and there are many, many SDKs available. So we picked one, and we were good. Okay, so that brings us to the first real problem we had to solve when we were thinking about this, which is how do we handle the typical process interaction, right, between two pods? So recall, we're coming from a local environment where we think of everything as sort of CLI processes and we're composing them. And now what we have to do is do it in the kube environment, right? Where the lowest abstraction we can reason about is pods. And this is also difficult because there's no guarantees pods are scheduled on the same node, right, in kube. And in fact, that is a bad assumption to make. So what we're trying to figure out is, how do we do something like this? You have your read CLI in the read pod, the write CLI in the write pod. How do we get them to talk? So what we realized was, taking a step back, you can actually restate this problem as a networking problem. And when you view it from the networking lens, it becomes much easier. The problem now becomes, okay, how do I create a connection to a remote IP port? And how do I wrap the main container's standard streams in a network protocol, right? Networking has done this for decades. There are many, many ways to do this. And what we found was socat. So if people are not familiar with this, there are two sort of very popular Linux networking tools. One is Netcat. I think that has more mindshare and more sort of developer usage. And there's socat, which is Netcat's more powerful brother. So we picked socat. What socat is, similar to Netcat, it takes a pipe and it turns it into a sort of networking protocol. You can do a whole bunch of stuff with it, very fully featured. So let's go through what this simple command is doing with socat, right? You have your read, again, your read CLI. And with this single socat command, we are able to take that output stream, wrap it in a TCP protocol, and shoot it to a remote IP port connection, all without writing a single line of code ourselves, except for using socat. So it's a great solution to problem one. So how this works is, on the right side, right now you have the write CLI, you say, listen to this port, 9000. On the read CLI side, you say, hey, read CLI, instead of only reading, take your output, use socat, and shoot it as a TCP connection to the right side of this entire pipeline. So that works great. We've kind of solved how to talk between the pods. But what we have also done now is made socat a runtime dependency. And if we all recall, right, one of the important things about the Airbyte protocol, or how we think about solving this problem of integrations, is we want to make it as easy as possible for people to contribute. And so we don't want any runtime dependencies. We want people to be able to submit any containers containing any sort of code in any language, and us to be able to run it. So this leads us to problem two, which is, how do we include socat without any runtime dependencies? And as this nice Wallace and Gromit picture shows, we can do so with sidecars. Again, I think not reinventing the wheel, very well-known concept, right, in software engineering. And how this works is, instead of bundling socat with the main container, we put it in a sidecar container, and we take the main container, wrap its entry point, and shoot it to the sidecar container. And then now the sidecar container does the same thing that we just talked about in problem one, right? Wraps it in TCP, pushes it to the right side. So you will notice question marks in my diagram, because now we have a third problem, which is, how do we pipe data between the sidecar containers and the main container? And so now we have solved the problem of, okay, how do we do it between pods? But we have shifted that sort of to, how do we do it within one pod, right? Because the problem here is that all these containers in Kube, they are not aware of each other, and they have their own entry points, and there isn't even a sort of parent process in Kube to do this orchestration for you, right? So you couldn't do something like this. You couldn't use the Linux sort of redirection operators and just say socat container, redirect yourself to the main container, or vice versa. So our solution to this is another tool from Linux, which is called name pipes. Kudos to Michel, our CEO. He was the one that suggested this in one of our design sessions. And for people not aware, name pipes are essentially pipes. So the pipes we've been seeing in the commands, they appear in file systems. The only difference is when you write to them, you're not actually writing to disk, you're writing to a buffer, right? And their sole purpose is to hold that data for a while someone else or some other process reads that out of the buffer. The fact that they're named means that they're very suitable for programmatic sort of use cases and scripting, which is what we do. And so you will see this later on in our live demo, where you will see all these names are actually all in setup scripts that we are using when we deploy Airbyte Cube. This works great in a pod, like among containers, because we have local file access, right? Cube pods, all containers in a cube pod are deployed to the same node. So assuming local file access is a good and valid assumption here. So let's briefly go through how this works in case people are not that familiar with name pipes. So let's assume I create two name pipes, a standard error pipe and a standard out pipe. Now, using the Linux redirect operator, I can say, hey, read command, I want you to pipe your output streams into standard error pipe and standard out pipe accordingly in the main container. In the sidecar container, we can now say, okay, you who are responsible for socat, right, you will read your input from one of these pipes. Right? In this case, this command is reading it from the standard out pipe, and then using socat and what we've already discussed to push all of that as a TCP connection to remote IP port combinations. So the last piece to using name pipes is now how do we create the name pipes? And this is actually pretty simple. We can do so using init containers. And again, this is wholly within Cube abstraction. Pods have containers. There's also an init container that runs before all containers are run in a Cube pod. And the purpose of that container is to essentially set up the environment for all the other containers to work. So we can use that to guarantee that our name pipes are created. Great. So that was a whirlwind through all of that, the three problems we had to come up with our ideal solution. Just a quick recap. We talked about how we pipe data between pods. We can use socat for that. Talked about how to bundle socat with our containers. We can use a sidecar pattern for that. And lastly, we talked about how to pipe data between our two containers. And we can use name pipes with an init container for that. And so now this leads us to this deceptively complicated diagram, which we will walk through. It's deceptively complicated because it's actually, thematically very similar to what we had when we first started, right? Remember this diagram? You have three processes with your worker orchestrator, reading and writing from the source and destination. So let's talk about this so everyone understands how this looks like on an architecture diagram. So, one second. So the most important thing, again, is the worker pod. Right? It does the same thing, create your source and destination processes, the read and write CLIs, how we think about it. In this case, they are backed by pods on Cube. Right? And everything we just talked about, all those techniques, comes together to let us think about this as a local process when under the hood is distributed. Right? So you have your init containers creating the name pipes. You have your main container with the wrap entry point piping as output into the name pipes. And then you have your sidecars taking all their output from the name pipes and pushing it to remote pods and enabling the processes to talk as though it's on one local instance. Yeah, so because of that, we can do the same we can apply the same thinking with composing CLIs within Kube and horizontally scale this, right? And so the same sort of data pipeline we saw earlier can happen, where data is flowing from the source through the worker all the way to the destination via the CLIs we're composing. Okay, cool. Now I'm going to try my hand at a live demo, and we'll see how that goes, just to let everyone see how this works in practice. So this is Airbyte, which I have set up locally on my laptop. I've already set up what we call a connection, and that is essentially a configured data sync job, so a configured way to move data from one source to one destination. So what I'm going to do now is kick off a sync, and then I'm going to switch over to my terminal. And just to clean things up, I'm going to remove all the completed pods from when I was testing this out. Okay, so you see in here the number of the running pods in my Kube cluster today. You see the orchestrator being created. We call it orchestrator, but it corresponds to the worker process that we were describing previously. And so this is already completed because it was a local test sync with not that many records being moved. But you can see what it created was your read process and your write process. So your read CLI and your write CLI. And so let's take a look at one of these pods just to see what makes up that pod. So bear with me while I scroll a bit. All right. So you see the init containers. And in here, we're making our pipes, as we discussed. And there's a whole bunch of other bookkeeping that's going on. Then we have our main container that, like we said, has its entry point being overwritten. Right? So we're running something, and then we're running a command, right, to start the container, and then redirecting its pipe somewhere else to the name pipes we create. And lastly, like we covered, we have our sidecars. So here you have a sidecar that is the standard out sidecar. It is running the exact same command that we had in the slides, where it's looking at the name pipe and using socat to push that as TCP to a IP port combination. Okay. And so I also want to show the logs from the worker, which we call the orchestrator. So if I take a look at the logs, you see output from both the source and the destination in here, right? So this shows that this whole mechanism actually is working as it is intended to, where what we saw on the diagram in here is happening. So everything is orchestrated by the worker, or in our case, the orchestrator, which I think is pretty cool, because what we just did was take a problem, solve it using existing tools and approaches, and reinvent it as little of the wheel as possible. So I just want to go through a couple of gotchas in case people are thinking of sort of playing around with this approach as well. So the first gotcha we ran into was startup tuning time. So we initially saw anywhere from 30 seconds to a minute of startup time as we started our Kube pods. And for us, that's because all this was running a JVM, and JVMs are actually very compute heavy, so we weren't giving it enough CPU to load all the classes fast enough. Once we figured it out, we got it down to 4 or 5 seconds, which is what we're very happy with today. The second thing we ran into was correctly propagating EOF signals and/or file signals. So for people not familiar, the EOF signal is a Linux signal that terminates connections, right? So it terminates your streams, it terminates the TCP connections that we just saw, and socat actually propagates this as well. So what we ran into was we were not correctly propagating this EOF signal sometimes. And so we saw hanging jobs in certain cases. So that was a bit hard to track down because it's a distributed bug. So yeah, be aware of it. The last gotcha we ran into was not using the kube watch API to check for kube pod status. So recall that our processes are backed by a pod. So when you start a process, you're starting a kube pod, and you need a way to figure out, okay, is this pod actually running? And equate that to your process status. What we started out initially doing was using the basic kube API and essentially DDoSing our kube API server as we repeatedly kept on checking. So a better way of doing this is using the events API to listen to events kube emits. And once we did so, this is running beautifully now. All right, so just a quick summary of what we covered today. First, we talked about how you can sort of think about syncing data as composing CLIs, your read CLI, your write CLIs. And then we covered how we can use all these Linux tools and concepts to horizontally scale CLI composition on Kube. And this is like simple, reliable. It powers hundreds of Airbyte Kube deployments every day. Airbyte Cloud runs on this, and we run at least 1,000 jobs a day today. And it works great. So yeah, that's all I wanted to cover today. Any questions? No? All right. Thanks, everyone. Appreciate the attention.